We're going to talk about RF devices or RF components. And some of the things we're going to talk about include cavity filters, duplexers, diplexers, circulators and isolators, cavity combiners, hybrid combiners, control station combiners, receiver multicouplers, tower top amplifiers, and pre-selector filters. So this is all really good stuff because we're going to take the information about these devices and how they work, and then the next module we're going to talk about how do we use them to work with interference issues in the field. So hopefully this will be useful to you. So the first thing we'll talk about is cavity filters. If you've ever seen a cavity filter, it basically looks like a big tin can with a rod coming out of it. And that's basically what it is, an empty can with two connectors on it, one that goes in, one that comes out, and the signal resonates inside the cavity. There's a plunger down the middle that is used to tune the cavity because its physical position, as determined by the plunger, determines what frequency it resonates on. So depending on whether it's a bandpass filter or a notch filter, by tuning that adjusting rod on the threaded rod, moving that plunger up or down, is how you tune it to a specific frequency. So we have an adjustment knob in the middle, and sometimes there's a second one for fine tuning. So the threaded rod goes up or down to tune the cavity. The plunger is what goes in there and adjusts the mechanical tuning. That determines what the center frequency is. So if it goes down, it lengthens the cavity and lowers the resonant frequency. If it goes up, it shortens the cavity and raises the frequency. The coupling loop is basically a connector with a little piece of wire on the end that acts as an antenna. The signal goes in, resonates in the cavity with the magnetic field, and then is coupled out the other side. And you would think there's a lot of loss in these cavities since there's not a physical connection, but when properly tuned, there's very little insertion loss. Here's what it looks like when you take it apart. The coarse tuning knob, the fine tuning knob. There are the little bandpass loops with the connectors on them. Stationary probe, movable probe. So X being the length of the probe should be equal to a quarter wavelength at the resonant frequency. So for example, if we had a cavity we wanted to tune at 406 megahertz, then that length at the internal probe would be 7 inches long. And of course, VHF cavities are much bigger and 800 megahertz cavities are smaller. So how does it work? In the case of a bandpass cavity, one end of the coupling loop is grounded. So this completes the RF circuit. So it goes in to one connector. The magnetic field resonates inside the cavity, is picked up by the second coupling loop and goes out. But it only has a tight coupling at the resonant frequency. So how does this look like on a graph? Here's a picture of what a cavity does on a graph. This is a bandpass cavity. In the blue is the insertion loss. So we lose about, even at frequency, we lose about 1 dB attenuation for insertion loss, which is not too bad considering you're not physically coupled from one end to the other. And then you have the bandwidth of the cavity. This is represented by the plus and minus points that are 3 dB down, which is to say half power, down from the peak, and the distance in bandwidth represented by the 3 dB points is equal to the bandwidth. So in this case, we have the 3 dB bandwidth, we have 4 dB down, we have 4 dB attenuation over a 3 dB bandwidth. And that's what a bandpass cavity does. It passes only signals on or close to the center frequency and attenuates everything else. So here's another drawing of how it works. Looking from the top, your signal source goes in one connector. It resonates inside the cavity at the resonant frequency as shown by the curve. This is actually a very sharp curve shown on the drawing here. There's very little attenuation at the resonant frequency, like less than 1 dB attenuation at the resonant frequency, but has a very high attenuation as you get off frequency. That's why this makes such a good filter. Series attenuation increases as the impedance increases. So this will be a very useful device, as we'll see. Here's another bandpass response curve, not quite as sharp as the one previous, but also a good bandpass cavity. This drawing or series of drawings will show us what happens if we take two bandpass cavities and put them in series. So this red curve shows a single cavity that has 2 dB coupling loops. In other words, there's 2 dB attenuation with this one cavity. So what would happen if we were to cavities, since they're a series device, what if we took two of these and put them in series? Well, then we get the blue curve. So what this drawing is showing is that the red curve has one cavity with 2 dB loops, so it has 2 dB of insertion loss. The blue curve is two cavities with tighter coupling 1 dB loops, so they both have the same amount of insertion loss. So at the top of the peak, they both have 2 dB attenuation. But notice the blue curve is sharper and more selective than the red curve. So what this slide is telling us is that if we want to have a higher selectivity than a single cavity, we can put two or more cavities in series and make for a sharper curve. So it makes it more selective. So at the green line point, we went from 17 dB on the single cavity to 21 dB on the two cavities in series with the exact same insertion loss. So we picked up 4 dB just by putting two in series. What about the size of the cavity? Does that make a difference? Well, it turns out that if we go to a larger diameter bandpass cavity, we can make it more selective. So if you see on the left, we have the response curve, a single 10-inch cavity filter. And if you look at the left, we're down a certain amount there. If you look at the same, at the response curve on the right with an 8.5 inch or a smaller cavity, we don't get as good an attenuation or sharper curve as we do on the larger filter. So this is just trying to tell us that if we want better selectivity, one way to do it is to put two in series. Another way to do it is to increase the diameter of the cavity. So that was a bandpass cavity. The second type of cavity we're going to talk about is called a notch cavity or a reject. Unlike a bandpass cavity, which passes a certain frequency, a notch cavity to cut out a particular frequency or notch it out. And notice that it's wired differently. The second connector is not even used. The first connector is connected with a T connector so that it passes over it, but at the resonant frequency, it gets absorbed into the cavity. The signal that passes through gets at that frequency gets absorbed into the cavity as heat, and that's where your notch comes from. So very little attenuation because off frequency it pretty much passes through. But when it hits that one particular frequency, it will absorb the energy that it's tuned for. And that excess energy comes out as heat. And you can feel these cavities and they get warm when they're operating. You may hear the term about the Q of a cavity filter. Q stands for quality factor, and what it does is it describes how selective a bandpass cavity filter is. It's a dimensionless unit because it's expressed as a ratio, which is the center frequency by the bandwidth. So you can see as the bandwidth gets smaller, the denominator gets smaller, and then the Q gets higher. So a higher Q is a narrower and sharper curve, and the low Q is a broader curve. Now, is a high Q better? Well, not necessarily. It depends on what you want to do. If you want to pass one frequency and one frequency only, then you'd want a high Q cavity. If you wanted to pass a range of frequencies, you'd want a lower Q cavity. So again, it's a function of bandwidth and the center frequency. Another way you can change the Q, and we already talked about putting cavities in series or increasing the size of the cavity. These coupling loops can also be changed out for more selective coupling loops, or they can be rotated to provide tighter coupling. So that's what we mean by the Q of a filter. So that's what cavity filters are. They can be used by themselves a lot, but they can also be put together into other applications. And the first one we're going to talk about is a duplexer. And we talked about duplexers in our discussion of conventional repeaters. And we said that a repeater could either have separate transmit and receive antennas, or it can share a single antenna by use of a duplexer. And if you look closely at this picture, there are actually 6 cavity filters laid side by side, each one with its own tuning rod and a cable connecting them. And the next drawing shows the theory of what this is. So in a duplexer, what we're doing is taking a single antenna and we're creating high impedance and low impedance paths from the transmitter and the receiver so that they can operate together. So the red signal in this drawing represents the transmit signal. So we know that in the UHF band, we transmit on side and receive on the high side. So in this case, we have a 450 megahertz transmitter and a 455 megahertz receiver. The transmitter is going to transmit at 450 megahertz. So we can have a series bandpass filters on tuned for 450, or we can have 1 or 2 notch filters tuned for 455. And what that will do is provide a low impedance path from the transmitter to the star point. And the star in the middle, the signal can go 2 different ways. It can go out the antenna, or if it looks towards the other cavities, they're tuned to 455, so At 450, they look like a high impedance, so it doesn't want to go that way. So the transmit signal, just like anything, follows the path of least resistance and will go up the antenna. On the receive side, just the opposite occurs. The 455 signal coming in will come in, hit the star, and it'll decide which way it wants to go. Well, it sees all those cavities tuned for 450 in one direction and cavities tuned to 455 in direction. So it takes the path of least resistance and heads towards the 455 receiver. And there's different variations on how you can arrange these type of cavities and whether they be pass or notch or both. But this is the basic concept of how a duplexer works. So here it is graphically, where we see a bandpass duplexer. It's passing the red transmit frequency, and then 5 megahertz away, the receive side is passing the receive frequency. And they have a high attenuation for each other at the wrong frequencies. This drawing is a pass notch duplexer where we have both band pass and notch together in series. So you'll see both the red and the blue line have a pass component and a notch component. And this will enhance the operation of the duplexer by providing a greater separation between transmit and receive frequencies. So this is much better than the previous one where all we had was bandpass. Here's another representation of bandpass duplexers where instead of very selective curves on a single frequency, we have lower Q cavities with wider bandpass that could pass a range of frequencies. Now you may have heard of a diplexer. It sounds like duplexer, but it's a different kind of device. A diplexer works on the transmit side and is used to combine outputs of two transmit signals in different bands to use a single antenna. So in this case, we have a diplexer that can pass both a 700 megahertz signal and an 800 megahertz signal to feed a single antenna port. And so that's commonly used in the 7 and 800 megahertz band. Also provides some noise filtering. It's basically two bandpass filters together. And now we're going to talk about circulators and isolators. They're really two different flavors of the same thing. What they are is they're used to route the radio frequency traffic and isolate devices. They provide impedance matching. They isolate from high unwanted signals. They also allow the monitoring of reflected power. So let's look at what one of these things looks like. Here they are, circulator and an isolator. You'll notice they're both the same device. The only difference is the isolator has a dummy load on port 3. And what the circulator is, if you were to take it apart, there's a couple chunks of powdered iron ferrite pressed together, which has the characteristic of only allowing radio frequency travel in a single direction. And so they're positioned so that it's a 3-port device that acts a little bit like a traffic circle. You know, if you drive these traffic circles, you know you're only supposed to go in one direction. If you go the wrong direction in a traffic circle, you will encounter a lot of resistance from the other cars coming at you. So you want to stay in the right direction. That's how a circulator works. If you put a signal into port 1, it wants to come out port 2. If you put it into port 2, it wants to come out port 3. And if you put it in port 3, it wants to come out port 1. So you can see everything moves in a clockwise direction. And so it acts as a flow control device for radio frequency signals. The isolator is the same thing, but you put a dummy load on port 3, which absorbs any energy that comes from port 2 to port 3, doesn't allow it to go any further. And we'll see how that becomes useful. So what does the circulator do? So in the forward direction, it has a very low insertion loss, low attenuation, on the order of a quarter of a dB of insertion loss. So port 1 to port 2, port 2 to port 3, or port 3 to port 1, whatever port you put it in the direction, it only has a quarter dB of insertion loss. There's 1 to 2, 2 to 3, and 3 to 1. No matter which way, it still has a forward attenuation of a quarter of a dB. What about in the reverse direction? Well, that's what makes it useful. In the reverse direction, it has a high attenuation. So we're looking at the order of about 25 dB in the reverse direction. So port 2 to port 1 is going to be 25 dB. Port 1 to 3 or port 3 to 2, anything going in the opposite direction is going to have a high attenuation, a high loss. So how do we use these? Well, this application, you could call this a poor man's duplexer, because look at what it's doing. It's taking a transmitter and a receiver and letting them share one antenna. Well, how does that work? Well, the transmitter puts the signal out into port 1. The low impedance path is from 1 to 2, so that's where the transmit signal goes. And it goes out to 2, and it goes out to the antenna. An incoming receive signal will come in, hit port 2. The low impedance direction is port 3 to the receiver. So it's kind of like that traffic circle. If you want to go to a particular direction, you have to go in the right direction, and you can manage the flow of traffic. But this really isn't used this way as a duplexer because it's not as good as a real duplexer. So what's an isolator? Well, an isolator is a circulator where port 3 has a load on it. So it really is only used with a transmitter. So you put a transmitter into port 1, it will take the low impedance path out to port 2 to the antenna. The reason it's useful is sometimes antennas don't work the way they're supposed to, and some of the signal is reflected back towards the transmitter. And that's bad for the transmitter, and it's bad for the signal. What we want to do, if there's a short or something wrong, a high SWR on the antenna, and that signal some of that signal gets reflected back, we don't want it to go straight to the transmitter. So it goes into port 2 and it heads towards port 3 where it gets absorbed in the load. So that's why it's an isolator. It isolates the transmitter from any antenna faults and allows the transmit signal to only go in one direction. So from the transmitter to the antenna, it only sees a quarter of a dB of insertion loss. But if there's a reflected signal coming back from the antenna, it gets absorbed and only has and it has a 25 dB loss if it tries to go towards the transmitter. So the low impedance path it takes is towards the load where it gets absorbed. So you usually don't see these by themselves. You'll oftentimes see them in series because that will provide better isolation. So you take the output of port 2, and instead of going straight to the antenna, you go into port 1 of a second isolator, and then take the port 2 from that one to the antenna. And then each one will have a dummy load on it. But notice that the one closest to the antenna has a bigger load on it than the first one. So the second stage isolator needs to have a load that's that's rated for the full rated power of the transmitter. And the reason for that is, let's say you have a 100-watt transmitter. It goes through isolators 1 and 2, only has a half dB insertion. So what if you have some kind of short circuit on your antenna to ground, and reflects all the power back? You need to be able to absorb all that power that's reflected back, and that's why you use the full rated load. But some of it will still sneak through from 3 to 1 and go into port 2 of the other one, and that residual power will then get absorbed by the smaller load in the first isolator. So that's called a dual isolator or a two-stage isolator. And you'll see these all the time, and they're used as a part of a transmit combiner system to provide translation. So here's one application they get used. If you want to keep a nice clean signal and keep that transmitter noise down, you can build a system that has your transmitter. It goes through your dual isolators, and then it goes into your cavity filters, where it either passes the signal you want or notches the frequency you don't want, and then goes to the antenna. I'm going to talk about this when we talk about intermodulation interference, how we can use these isolators and cavity filters. Okay, we'll pick up where we left off. I hope everybody had enough time for lunch. And I don't know what time it is where you are. It's 3:30 here, but I know on the West Coast it's probably 12:30. All right, we'll pick up on the slide where we were talking about isolators. And if you recall, an isolator is a 3-port device that is used to isolate a transmitter from an antenna. You feed the signal into port 1, it comes out port 2. One thing to note about isolators is, because they are hybrid devices using ferrite, they do produce some harmonics. And we know a harmonic is a multiple of a frequency. So in order to reduce those harmonics, it's common to put a filter on the output, either a bandpass filter, a low-pass filter, or a specialized second harmonic filter for a specific frequency. So these will help to cut the harmonics by putting the filter on there. So let's talk about transmitter combiners. These are devices that will combine some of the things we talked about, and their purpose is to bridge multiple transmitters together to use a common transmit antenna. They have a couple secondary functions. They cut down on transmitter sideband noise because they employ filters, and they also employ isolators. So some things to remember about transmitter combiners. They do use cavities, so there's some cavity loss in there. We remember each cavity had about 1 dB of loss typically. There's also a bridging loss, and the bridging loss is from bridging multiple cavities together. This is normally about a half a dB per channel. There is sideband noise reduction provided by these cavity filters in a combiner. and we'll typically see about 45 dB sideband action. So they have some secondary functions as well as combining transmitters. So let's look at how transmitter combiners work. So you remember on a duplexer we had a combining point in the middle where you had the transmit side and receive side go to the antenna. Here we have in the middle of this diagram the hex-shaped device is just a mixing point where everything is connected together. In this case, it's a 5-channel transmit combiner. What we have, if you go around the circle, we've got 5 transmitters. Each one has a dual stage isolator between the transmitter and a cavity. The purpose of the isolator, remember, is to isolate and remove any energy that might come back towards the transmitter to protect the transmitter. Then we also have a bandpass cavity. Each of these bandpass cavities will be tuned to the frequency of that transmitter. And so what we've done by combining them is to provide a low impedance path from any one transmitter to the antenna and a high impedance path from any transmitter to transmitter. Because as it looks, it goes through the isolator, no problem. Half a dB loss there. Goes through the bandpass cavity, which is tuned to its frequency. Maybe a dB loss there. Then it looks at the combining star and it sees high impedance everywhere except for the low impedance path out to the antenna. In addition to that, we're going to take advantage of the lengths of transmission line when we put the combiner together. We know that transmission line acts differently depending on the length. If it's a quarter wavelength long, it looks like an open circuit. If it's a half wavelength long, it looks like a short circuit. 3/4 wave looks like an open circuit, and a full wave looks like a short circuit. So we'll take advantage of that when we put together our transmitter using specific lengths of transmission line. So here's a simple example where we have a 2-channel combiner. Each transmitter is connected to the 2-stage isolator, then through a bandpass filter. And then in order to get from there to the combining point, we provide a length of quarter wavelength transmission line. And that quarter wavelength transmission line is going to look like an open circuit, and it's going to pass through no problem, and it'll get to the junction point, the T in the middle. It'll see a low impedance path out to the antenna, but when it looks towards the other transmitter, it now sees 2 lengths of transmission line. A quarter wave and a quarter wave equals a half wave, and a half wave length of antenna, half wave of transmission line looks like a higher path. So in addition to the isolation provided by the isolator and the bandpass filters, we're also taking advantage of the length of transmission line to try to give us the high impedance paths to any other transmitter and the low impedance path to the antenna. So there's really 3 different things being used in the transmitter combiner to make sure that these high-powered signals don't feed into other transmitters. So here is the same thing, but in a form of a 5-channel combiner. So we see that from the perspective of transmitter 1, we have a quarter wave cable from the cavity filter to the combining point. So that looks low impedance and continues low impedance out to the antenna. But when it looks at any of the other 4 transmitters, it sees a combined half wavelength of cable and therefore sees a high impedance. And it follows the path of least resistance out to the antenna and doesn't bother the other transmitters. Here is a picture of a 6-channel transmitter combiner, rackable, and it has all the pieces we saw in the previous diagram. The, each one of those ports on there, there's 6 ports on there. Each one connects to a transmitter, and there's a dual stage isolator on there, and you can see that the blue cables coming out are the port 3 of the isolators. They go into a common heatsink load in the back of the unit. You'll see 6 tuning knobs out on top, and then beneath the cover are the lengths of transmission line, and in the very center you'll see a 7/16 DIN connector, which is the output going to the transmitter. So this is a rack-mounted 6-channel transmitter combiner. If we wanted to do a 10-channel combiner, which is not normal, typically we stick with 5 channels or less for each antenna. But if we did want to do a 10-channel combiner, we could take 2 5-channel combiners and connect them together. So now if you look at the way that the transmission lines are set up, we have half-wave length transmission lines from the combining points of each of the 2 5-channel combiners. So if you look at the perspective of any one transmitter, it sees a total of half wavelength between it and the antenna, or should I say 3/4 wavelength between it and the antenna, which looks like a low impedance. But when it looks at any of the local transmitters, it sees half wavelength, which looks like high impedance. And if it looks at one of the distant transmitters, it sees 1/4 plus 1/2 plus 1/2 plus 1/4, 1 full wavelength, and that looks like a high impedance path also. So again, by using the right lengths of transmission line, the signal will follow the path of least resistance and go out to the antenna. So that's a 10-channel combiner. We talked about insertion loss. Because it has cavities and bridging loss and cable loss, we have some insertion loss in the combiner. So it's not uncommon that a 100-watt transmitter will only allow 50 watts to go out of the combiner, but that's still plenty. So this diagram shows the different components of insertion loss within a transmitter combiner. The isolator loss, remember we had about a 0.5 dB total forward loss on the isolator. Then we have the cavity insertion loss, which could be from 1 to 3 dB. The cable itself has loss, and there's a bridging loss from bridging all these other components together. So that's a cavity-based transmitter combiner. But there's another type, see, and that's called a hybrid transmitter combiner. And this doesn't use any cavities at all. Instead, it uses the same kind of ferrite material that isolators and circulators use. And what that means is that it's no longer cares about the actual frequency. It will operate on a range of frequencies. So the advantage is it does provide a good 50 ohm match between the transmitter and the antenna. It's wideband, since there's no cavities, it doesn't care so much about frequency, and there's no minimum frequency spacing. On the cavity-based transmitter combiner, you can't have the transmit frequencies too close to each other. They can't be adjacent channels, for instance. There's just not enough isolation to take care of adjacent channels. So the specs on a transmitter combiner will typically give a minimum frequency spacing, but these do away with that. So there may be an advantage to that. But for every advantage, there's a disadvantage. And the big thing with the hybrid combiners is they have a high insertion loss on the order of 3 to 4 dB per channel uh, on a 2-channel combiner. For a 4-channel combiner, you're talking about 7 to 9 dB loss. So 3 dB, 3 dB is half the power, 6 dB is a quarter of the power, 9 dB is 1/8 of the power. So you lose a lot of the power in a hybrid combiner, but there may be times where it could be useful. There's also a window filter to cut out the harmonics, because just like an isolator, it generates harmonics. Here is kind of what happens inside a 2-channel hybrid combiner. It's kind of interesting to see how they do this. Each of these dots here is one of those 3-port isolators, and they're arranged in a diamond pattern with a load on one of the ports. And we'll show what happens when the signal goes from any one of the transmitters. So in this, on the transmitter combiner, how we took advantage of transmission line lengths, we're doing the same thing here. The line lengths inside are specifically cut so that we can attenuate certain frequencies. Of course, the hybrid itself doesn't care about the frequencies, but the transmission line length does. So we got 3 of them are quarter wavelength and 1 of them is 3/4 wave. So if a signal goes out from transmitter 1, it splits. One side goes through a total of a half wavelength of transmission line before it sees transmitter 2, which looks like a high impedance, so it doesn't like to go that way. If it goes the other way, it sees a total of a full wavelength of transmission line, and that looks like a high impedance path. So no matter how it gets from A to B, it looks like a high impedance path. The only low impedance path it sees is the one that leads to the antenna. So it provides a combination of virtual opens and virtual shorts. Again, the low impedance path being the one to the antenna. Here's an example of a 4-channel hybrid combiner. Again, there's no minimum spacing requirement, but the downside is there's a high insertion loss. Here's what they look like in the field. This is a 2-channel hybrid combiner with the 2 transmitter input ports, the antenna output port, and the load port. Now we have another type of transmitter combiner that's called a control station combiner. And a control station is a low-powered base station that's typically used to access a repeater for the purpose of typically interoperability purposes, not as part of your primary system. But if you are a public safety agency and you want to have interoperability with your neighboring agencies, it's common to have these control stations pointed at your neighboring systems, and you have a stack of these. And the problem is you don't want to have an antenna for each one, because you may have 6, 8, 10 of these things. I've seen stacks of 30 of these things at a site. And so you use one of these control station combiners to reduce the number of antennas when you have a lot of these control stations. And remember, a control station does both transmit and receive. So this is not actually a transmitter combiner. It's a control station combiner that works on both transmit and receive. So there's 2 different types of these. One of them works with only 1 antenna and one requires 2. But either way, it reduces the number of antennas required and provides some isolation. So the first type we'll talk about is called a short haul control station combiner. This is the type that only requires one antenna to operate. So here we have 4 control stations using one antenna. And the reason this is called a short haul control station combiner is that it has a lot of loss in it. So it only works with stations that are close by. And the rule of thumb is about 5 miles or less from the site, you can get away with using these. So you're looking at the order of 20 dB loss through one of these in both transmit and receive directions. So that's not so good, and that's why they're only used for short links. So the advantage is the isolation is not dependent on antenna isolation. The high insertion loss can work in your favor in that it cuts down on transmitter noise, and it is lower than other types. The main advantage is it only requires one antenna, but the insertion loss does cut down on intermod. The disadvantage, of course, is that it not only has low power going out, but it works in both directions, so it also cuts back on the receiver sensitivity. So it has a lot of attenuation on both sides. So that's why they're fine if you keep the distance to 5 miles or less. This is the second type of control station combiner, and this is the type that can be used on longer distances. It has separate transmit and receive antennas, and inside this guy is basically a bunch of circulators and isolators. So you'll see each control station has a circulator attached to it inside. Then there's a couple of isolators on the transmit side. So we'll follow the signal path through this to see how it works. On the transmit side, if any given control station transmits, it goes through port 1 to port 2 on the circulator, goes through the dual stage isolator, goes through a hybrid combiner, and out the transmit path. Not a lot of loss. What happens on the receive side? On the receive side, the signal goes in, goes to a hybrid splitter, goes into port 3 of the circulator, which takes you back into the control station. So this one has a lot less loss than the short haul combiner. So that's transmitter combiners and control station combiners. And the next thing we're going to talk about is a receiver multicoupler. And a receiver multicoupler is the opposite of a transmitter combiner, where a transmitter combiner will take multiple transmitters and combine them into a single transmit antenna. The receive multicoupler will take a single receive antenna and split it out to serve multiple receivers. So that's why you could have a 10-channel or a 5-channel trunking site with only one transmit antenna and one receive antenna. Here's a picture of the indoor portion of a receiver multicoupler. Some systems have an additional part on it called the tower top amplifier. And the reason they're called that is the amplifier actually mounts up on the tower close to the receive antenna. And they are used when you want to overcome long lengths of transmission line where you get a lot of loss. So they go right up by the antenna. They will feed a stronger signal through the transmission line, which then goes to the indoor unit to get distributed to the multiple receivers. There is a type of filter used in there called a pre-selector filter that is inside the tower top amp, goes between the antenna and the indoor preamp. And the pre-selector filter is a wide bandwidth bandpass filter that is used to sure you only receive in-band signals. So it might have like a 5 megahertz bandwidth on it. A tower top amp is there to overcome long transmission line runs. The indoor part, there's another preamp on the indoor portion. Its job is to amplify the signal to overcome the distribution loss, because you will be splitting the signal out 4 or 8 or 16 or 32 different receivers, so you got to overcome those losses. But most of the system gain actually comes from the tower tap amplifier itself. And we'll see how this works. Somebody made a comment you were looking at one of these yesterday. Okay. So here's what the schematic of what they look like. On the outdoor piece, close to the antenna, up on the tower, you probably won't notice it if you're not looking for it. There's an active amplifier up there. It goes down the transmission line and goes to a distribution amplifier. And again, the purpose of the first amplifier is to overcome line losses. The purpose of the indoor distribution amplifier is to overcome distribution losses. So the indoor unit amplifies and then divides. And in this picture, it shows 4 receivers, but you could feed many more if you want. Okay. So the type of gains and losses we're talking about, the tower top amp itself might typically be a fixed gain 20 dB preamp. Then you might have 8 dB of line loss, which would be a pretty long line to have 8 dB of loss, but it's possible. Then you might have a 12 dB gain indoor amplifier. Your total system gain then is anywhere from 8 to 15 dB, and you can adjust the gain of the indoor amplifier. But you don't actually adjust the gain in the amplifier, you put pads in there to bring it down. Up on the tower itself, you have typically a stainless steel box up there, and there's a pre-selector filter, which again is a wide bandwidth filter used to keep only in-band signals going. The receive antenna will feed that pre-selector filter, and then it will feed the transmission line going down. Now there's a couple other things you'll notice in this picture. First of all, the amplifier, the triangle there in the middle, since it is an active amplifier, it needs power to operate. So how does it get the power? Well, the DC power is actually sent up through the main transmission line, and there's a pickoff unit with an inductive coupler that will take the DC off and feed the amplifier with DC power. You'll also notice there's a second transmission line coming off of the pre-selector filter, and that is the test port. The pre-selector filter has a sampler in it that will take a sample of the signal and send it down for test purposes down below. Since this thing is up on the tower, you can't climb up there every time you want to check it out, so that's why there's a test port on there. So you might have a 7/8 inch main transmission line run and a 1/2 inch test line, because it's not carrying any amount of power. So the indoor unit.
Hey, Bruce.
Yeah.
I'm sorry. I got a quick question before you go any further. So,
Okay.
PDA system, like if I really want to tap into the receive end of it, right, before the distribution stage and everything, and if I tap into it, I mean, that will disable the TTA because it requires a DC power, right? So will I be able to actually look at the raw signal bypassing the TTA?
Yeah, let me back up. So if you look at the line on the right is the test line, and it's not the one that carries power. It's a totally passive line for sampling. The one on the left is the active line. That has the amplifier and the power on it. So you'll be able to sample the signal that's coming in. This is ahead of the preamplifier. So you'll be able to sample the raw signal as it comes in. You don't need power to do that. And that goes all the way down to the test port.
So, but I meant, say, if I disconnected the polyphaser and can I do it?
Yeah, it'll still work. The test line will still work because that test line doesn't require any power to operate.
Okay, that's what I thought. I was told by by company that the moment I disconnected it, I will not be able to see the raw signal because of the TT up there, and it will prevent me from looking into it. Didn't make any sense to me at that time, but now it
No,
makes.
if you look at the diagram, you'll see that the test line has no active devices and requires no power.
Good. Okay. Thank you.
It wouldn't be useful as a test port if it failed when the power failed.
Right. Okay.
Okay.
Thanks. Thank you.
All right. So into our part. So at the top, the main transmission line comes on. There's a T filter with the inductor to feed the DC power into the transmission line. There's a DC power supply. And in the middle, the triangle, is the fixed gain multi-coupler amplifier. And you adjust the gain on here. Since this is a fixed amplifier, the way you adjust the gain is putting little attenuators in the line to reduce the signal either ahead of or behind the amplifier. And then you will go to your distribution blocks and distribute the signal. In the example here, we show a 16-port multi-coupler where it first goes into a 4-way splitter. 2 of them go into an expansion port and the other 2 go into 8-way splitters. You'll also see the test port passes through the indoor unit right to the front panel. And if you go back a couple slides to the picture, you will see that BNC coupler on the right is the test port. That's where you could plug your spectrum analyzer in. Okay, the tower top amplifier also has a pre-selector filter. This particular type of filter is called a comb line filter, and it's basically like a series of cavities in series. And again, it is a pre-selector, so it has a wide bandwidth, anywhere from 5 to 30 megahertz. It also has a low insertion loss, and it does have good selectivity at the edges of the bandpass curve. So this is the best kind of filter to use for pre-selectors. And if you look, you'll see at the bottom left is the input line, the bottom right is the output line for the main line, and up on the upper left, you'll see a little BNC connector with a little sampler in it, and that's your test port line. So the test port sampling is done right at the pre-selector filter. So this drawing just shows how the another type, this is a different type of pre-selector called a bandpass notch, where the other one was purely bandpass. Go back. This was purely bandpass. This other one is a band notch filter, where it has 3 bandpass cavities and 1 notch cavity. So just a different way of doing it. Just like duplexers can be done either purely bandpass or bandpass and notch together. The tower tap amplifier requires power. So again, the way power is brought up there is through a DC power supply in the indoor unit, through an inductor into the main line, and out to the amplifier. And this is a typical type of DC injection type light polyphaser. You'll see the input and output lines, but you'll also see a connector that is used to put the DC in. So that's My last slide on this section